Okay, so I'm going to talk about Ramsey theory, which is actually in chapter 9. I consider Ramsey theory to be part of extremal graph theory, as do many people, but it's not in chapter 7 in the book. But anyway, so here's what it is. This is about coloring the edges of a complete graph. So RST, this is the Ramsey number, the capital R is for Ramsey, is the smallest value of n such that every red-blue coloring of the edges of Kn, meaning that I'm going to take a complete graph on n vertices and I'm going to color every single edge either red or blue. And every such coloring contains either a blue k sub s or a red k sub t. And when I say these things, I mean a blue ks is a set of s vertices such that every edge among them is colored blue, and a red kt is t vertices such that every edge between them is red. Yeah, so that's the definition. And this is a little bit different notation from the book. The book uses the notation R of k. There's just one parameter, k. And in this notation, that would be R of kk. That just means that S is k and T is k. In other words, you're looking for a blue set of k vertices or a red set of k vertices. It's just that S and T are the same. Anyway, let's go over some simple examples. R of 1 T would just be 1. This is kind of silly, actually, because a blue K sub 1 is just a single vertex. So as long as n is at least 1, if I'm coloring the edges of this graph, of course there are no edges, this entire thing is silly, but no matter how I color the edges, I'm going to find a blue K sub 1. How do I know it's blue? Because every edge is colored blue. Okay, let's stop being silly. Anyway, that's one. Let's talk about something slightly less silly, R of 2t. Now I am talking about the value of n such that every red-blue coloring of k sub n contains either a blue k sub 2, and a blue k sub 2 would just be a single blue edge, right? So I'm talking about the minimum value of n such that every coloring of the edges either contains a blue edge or it contains a red k sub t. If I have, and I'm claiming that it's t, and that's basically because if n equals t, then I have t vertices, and I've got two choices. If I color even a single one of these blue, then I have a blue edge. If I color them all red, then I have a red KT. So no matter what I do, I have one of these two things for n equals t. Also, that's the minimum value of n, because if n was less than t, then I could just color all of the edges red, and I wouldn't have either of these two things. So this one is exactly t. All right. And then I guess the next natural thing to talk about would be R of 3t. That one is where it starts to get really hard. Like Ramsey theory becomes very difficult very fast. The R3t is, should be some function of t. It's unknown. There are some bounds on it known. The bounds involve logarithms, which is very strange. but, well, it's not that strange once you get into this type of stuff. If you notice on the left and right, we have the same, it's like the same function. It's like t squared over log t. It's just times two different numbers. And what I mean by this epsilon, I mean for all positive epsilon, there exists sufficiently large t. This is a statement about sufficiently large t. Give me any epsilon greater than 0, and then for t large enough, this inequality holds. Anyway, maybe this is getting ahead of ourselves at this point, but it starts to get interesting fast, and actually a lot of work was put into both of these bounds. These bounds are like successive improvements and improvements by, famous mathematicians, and this number is still not known very well. Anyway, let's get to a more concrete one like R33. Again, some of you have seen Ramsey theory before if you took combinatorics with me, but for some of you it's new. I'm saying that R33 equals 6. First of all, so what does verifying this really mean? I have to say that this is the minimum value of n, such that every red-blue coloring of the edges contains either a blue ks or a red kt. And there's naturally two parts of that. You have to show that if n is smaller than this number, for example, if n is smaller than 6, then it's not the case that every red-blue coloring has a blue ks or a red kt. In other words, to show that, we have to come up with an example of a red-blue coloring that doesn't contain a blue ks or a red kt. For us right now, that coloring will do. If n is smaller than 6, for example, n could be 5, I could color it this way. And you can check, this does not have a blue K3 or a red K3. There's no blue triangle and there's no red triangle in this picture. Of course, if I can color this for n equals 5, I can also do any smaller value of n. Here, look, I'll do it for n equals 4. I just cover up that vertex. So to check this, you really just check for n equaling 1 smaller than this. So if I can do it for n equals 5, that's good enough. The other half of verifying that this equals 6 is to consider what happens if I did have n equals 6 and show that it's no longer possible. In other words, no matter how I color this red or blue, I will always have a red triangle or a blue triangle. And I'll go through the proof with you. A lot of this proof is just going to be me talking out loud instead of writing things, so hopefully you'll listen. Pick any vertex, V. V has to have edges going to 5 other vertices. And they all have to be either red or blue. So out of these 5 edges touching V, some of them are red and some of them are blue. Whichever color has the most has to have at least 3, right? Because I have 5 and they have to be split in between 2 colors. So there has to be a color where 3 of them are that color. Without loss of generality, assume that that color is blue. There's 3 edges colored blue, and assume that there are these 3 edges. Now what can happen? In fact, let's just focus our attention here. This can't be blue because that would make a blue triangle, so it's got to be red. This can't be blue because that would make a blue triangle, so it's got to be red. This can't be blue because that would make this blue triangle, so it's got to be red. Oh no, we just made a red triangle. So So this is it is impossible to color that graph. We just out loud we said without loss of generality, and we checked every possibility, and it's just not possible to check this, to color this one, and avoid red triangles and blue triangles. Okay, so those are some basic Ramsey numbers. But actually this is a question that we sort of glossed over. It's kind of easy in math when you define something, it's sometimes it's too easy to accept the definition. There's a real question as to whether this exists. Just because I wrote a quote-unquote definition doesn't mean it actually exists. Specifically, I defined it as a minimum value of n with a certain property. What if there's no values of n with this property? Right? In other words, what if no matter what n is, there exists a red-blue coloring of the edges of Kn that doesn't contain a blue Ks or a red Kt? I mean, without proof, I mean, it's not entirely trivial that's the case. It is the case, and that's Ramsey's theorem. So let's prove that. So this is going to be by induction. It's a little bit of a funny form of induction. It's induction on S plus T. So the induction hypothesis is that R of S prime T prime exists whenever the value of S plus T for that, meaning S prime plus T prime, is smaller than the value of S plus T for the S and T that we're considering. That's the induction hypothesis. Then what I'm going to do is I'm going to show that this set is not empty. This R of ST is defined to be the minimum value of n that has this property. So there's some set of n that has this property, and as long as that set isn't empty, it has a minimum member. So I'm going to show that there exists an n with this property. In other words, an n with the property that every red-blue coloring of its edges must contain a blue Ks or a red Kt. In particular, it's going to be this value of n. And this is a legitimate value of n that I can point to because of the induction hypothesis, right? And this one, I can look at it like S prime is S minus 1. Maybe I'll sneak that in there. And then T prime would be T. And S prime plus T prime is strictly smaller than S plus T, right? If I add this up, it's actually S plus T minus 1. And then similarly over here, I can call this S prime and call this T prime. But the point is, their sum is smaller than S plus T. So this is a value of n that we are sure exists by the induction hypothesis. And I'm claiming that this value of n has the property that we want. In other words, every coloring of its edges contains either a red, a blue. Okay. Start over. Every red-blue coloring of its edges contains either a blue Ks or a red Kt. So here's the proof of that. Pick any vertex, and then, of course, it has like what I can call its blue neighborhood and its red neighborhood, because we're coloring the edges of a complete graph, so there's edges going to every other vertex in the whole graph. I claim that either the blue neighborhood contains at least this many vertices, or the red neighborhood contains that many vertices. So why is that true? Well, if this one contained strictly smaller than this many vertices, and this one contained strictly smaller than this number of vertices, then just count the number of vertices in the whole graph. I would have this minus 1 plus this minus 1 plus 1 for v, and that would be strictly smaller than n. So that can't happen. So just because n is what it is, either this set of vertices is at least this large, or this set of vertices is at least that large. But then we're done, because we can check a couple of cases. If this set of vertices is at least this large, what does that actually mean? That means that if I look inside this bubble, either I see a blue k sub s minus 1, and if I see a blue sub k sub s minus 1 in here, then I can see a blue k sub s when I put in the vertex v, because I have this blue k sub s minus 1 sitting in here, and v's edges to that are all blue. So if I see that in here, I'm done. The other thing I might see in here, because I don't know which one of these things I see, I'm guaranteed that I see one of them. And the other one would be a red k sub t, and if we see that, we're immediately done. The other possibility is that this set of vertices is at least this big, and this finishes it off entirely analogously. So this would imply either I see a blue k sub s, in which case I'm immediately done, or a red. I forgot to write the word red here, but let me go back down here. I could see a red k sub t minus 1, and if I saw that in here, I would be done, because that would make a red k sub t with v. And that's the proof that Ramsey numbers exist. So we are now, we've defined these numbers. We had this surprise question about whether they even exist, which is always interesting after you've already defined something. And now we know that they do exist. So now the question is to find them, or at least estimate them. That turns out to be incredibly hard in general. So let me say the first thing along these lines is that the proof that we just went through, that these numbers even exist, if you pay attention to the proof, we actually proved an upper bound on the Ramsey number, because, of course, let's go back through the proof. We showed that this value of n is a suitable value of n to go here in the definition of RST. In other words, it's a value of n such that every red-blue coloring of the edges of Kn satisfies blah, blah, blah. That value of n may not be the minimum value of n, but it is a suitable value of n. Whatever the minimum value of n is, it's less than or equal to this. So the minimum value of n is less than or equal to the value that we put. In other words, the actual R of ST is less than or equal to that. It's less than or equal to what we put. That implies by induction that R of ST is less than or equal to 2 to the ST. I can just out loud, I'll go through this proof of induction with you. It would be another proof by induction on S plus T. And by the induction hypothesis, you would get that this one is at most, so many smudges on this paper. This was looking so pretty, but then I'm making it ugly. This one would be at most 2 to the s minus 1 plus t, by the induction hypothesis, this one would be less than 2 to the s plus t minus 1. And then by the magic of algebra, that equals 2 to the s plus t. And so that's basically your rough proof without writing very much on the page, rough proof by induction that we have this upper bound on R of st. Okay, but I mean, and that's nice. Now these numbers are a little bit more than just these obscure things, and all we know is that they exist. We have an upper bound on them, but we would like to estimate these numbers. So maybe a lower bound would be nice to have. Okay, so actually, maybe now I should probably cut this video off and start a new video just on general principles mostly. So let me do that at this point.